Alright, so today it's day 44, and essentially today the only thing that I did was the implementation of this. I already did the implementation, but I make it even simpler, like a really easy demo of this paper, which essentially it's a deep dynamic latent block model for clustering of zero inflated data matrices. The code is this one. I don't know if I already explained, but I can explain quickly like this implementation. Sorry for the color theme. I'm gonna change it. Where is it? All right. So for the implementation, we basically have the nature of the data we have. It's a bipartite graph, so you can express the data as connections of nodes, some source to some destination, and this connection is modeled by a probability distribution. But it's like the model is not between nodes, but rather between blocks of nodes. So you can assign a label, like a cluster, to the rows of the nodes and to the columns, and then you can understand the dynamics of how the rows interact with the columns when they belong to a certain group. That's like the basic intuition. So essentially we have like some observations. Okay, I'm gonna give a concrete example. A concrete example would be you have these 100 stations beginning and you have 100 stations destination, and you want to understand like the behavior of the network, right? So these are like travels that people make with bike at a certain amount of time, and then you count them like at time zero. Like if somebody took like a travel from node 0 to node 12, you do it like you count all the travels at a specific time, and if you do it for all possible times, you have like a tensor, right? And the thing is, like, you want to estimate the behavior by classifying this into a cluster and understanding the distribution. And the way to do it is like I initialize the data, right? I need the most important parameters is this one. This defines the interaction. Then we have also alpha, which defines like the proportion of the row clusters, then beta of the columns. Then we have some sparsity. That's like the novelty of the model. The novelty of the model is that it's latent. It's a latent block model. It's block model, so it involves co-clustering. It's dynamic. It evolves through time, and it has accounts for sparsity. So this is a parameter we account for in sparsity. But when we compute the EM algorithm, we add other types of parameters. All right. So the initialization is just like sampling some realizations. In this case, we assign randomly based on alpha, and alpha is a parameter. It's like a vector. So at every time step, we have a vector of size of the amount of clusters, and we assign a probability of like the proportion, like how likely is a node to belong to a certain cluster. We do this for the rows, right? We do this for the columns, and then we sample because we have like a rule. We say that if there is a node that goes from a cluster 1 to a cluster 2, then you have to use the specific rate defined by the lambda, which is the matrix of size, amount of clusters times amount of cluster. Yeah, and we generate the data set. Also, we mask the zero values, so we have like a average of. We have to account for sparsity, which essentially we are saying in this specific model, I say the network degrades over time, so the sparsity increases. And then you have to be able to differentiate between the zeros that are structural zeros or because of the sampling in the distribution. You assign like a posterior probability, and based on this you like understand the behavior. I used like neural networks, right, for estimating parameters. This is the initialization, and then we just do the variational step, right? So it's first day step in which given that this was already initialized, we update this and we can use the formulas, which are like a really mathematical long derivation. The good thing is that they are already implemented in the paper, so you can just copy and paste them in the code and apply them. Although sometimes I use like some heuristics just for just to not use so much computational power. That's it. So for example, this is not exactly a formula. It's like heuristic because it's an aggregation, right? So the properties of the matrices are not. You shouldn't do this exactly as I did, but it's okay. I'm just this is just a sample code. So basically, we have this. The interpretation is basically this is the alpha. This is how, because we have like some matrix. This matrix has like some clusters, hidden clusters, and these clusters evolve through time. And then this cluster size changes like by a true sampling distribution, by a sine wave that I said, which is this one. And this model is able to predict this specific line, the orange one. And also the sparsity is a linear, holds a linear relationship with time, and also it's able, the model, to classify it. And that's essentially it. I also implemented with differential equations with neural nets, but that is much complicated. And I got like a buggy result, like this one, especially for the sparsity dynamics. But yeah, that's it.